Alright, so in this video I'm going to be explaining another important article with the title Representation Learning on Heterostructures via Heterogeneous Anonymous Walks. This paper in 2024. Capturing structural similarity has been a hot topic in the field of network embedding recently due to its great help in understanding node functions and behaviors. However, existing works have paid very much attention to learning structures on homogeneous networks, while the related study on heterogeneous networks is still void. In this article, we try to take the first step for representational learning on heterostructures, which is very challenging due to their highly diverse combinations of node types and underlying structures. To effectively distinguish diverse heterostructures, we first propose a theoretically guaranteed technique called heterogeneous anonymous walk and give two more applicable variants. Thus, we devise the HAW embedding and its variants in a data-driven manner to circumvent using an extremely large number of possible walks and train embeddings by predicting occurring walks in the neighborhood of each node. So you see examples of HAW and overview of the proposed HAWE. The node shapes denote node types. The walks in the same color captures the same heterostructure. And so we find the distinguished heterostructures. For example, a type of this is connected to a type of this square. And this is synthetic pinwheel networks. Node shapes denote their types, and node colors denote their structural roles. So structural role-based NE has attracted increasing attention. It is worth noting that a series of them are developed based on anonymous walks to generate structural embeddings or enhance the hot field of the graph neural networks, because it is theoretically proved that neighborhood structures of a node can be reconstructed with anonymous walks starting from it. So there are four contributions in this paper. We are the first to directly study NE that captures heterostructures. We proposed a novel HAW which has theoretically guaranteed on reconstructing heterogeneous neighborhood structures, provide an effective heterogeneous structural NE method, and we give the first benchmark on heterogeneous learning. So the problem is a heterogeneous network, which is defined as this, where nodes V and edges construct the topology. Phi maps each node to a node type, and psi maps each edge to an edge type. So we have node types and edge types. They are not homogeneous, they are heterogeneous because there are more than one node type or more than one edge types. So I've explained these random anonymous walks in the previous videos, so we skip them. And so this is important, that to know the definition of heterogeneous anonymous walk. that here is the definition of that. Given a random walk occurring in a heterogeneous network, its corresponding heterogeneous anonymous walk is the L-length sequence of two tuples, where the tuple is f and psi. F and phi. So how do we do this embedding? Like learning language models, we need to generate the heterostructure corpus first, because we want to do something like graph, word2vec and those things. So we need to have a corpus. For each paragraph node in a given heterogeneous network, we sample a sequence of heterogeneous anonymous walks starting from it as its context word. So we have a corpus C, and the size of L, which is a lexicon over the corpus, is always smaller than that of the total corpus, since there are many common heterogeneous anonymous walks overall context. So we find the probability here. We train by maximizing the average log probabilities for our words occurring in the corpus, where each probability is computed via softmax function. So the same idea, these are the context, and you try to maximize this condition on the context. And the unnormalized prediction probability now can be computed like this. But in practice, we can only sample a limited number of heterogeneous anonymous walks, so some key heterostructures could be missed. For example, the bridge edges should be more important than non-bridge edges for the involved nodes, but are more difficult to be sampled due to their low frequencies. So we draw lessons from node2vec that I've explained in a different video, and use two positive parameters to bias heterogeneous anonymous walks. So in a random walk having just traversed the edge, the unnormalized transition probability from node V to one of the neighbors V prime is in this step. It is in this formula number 5. So P and Q control the heterogeneous anonymous walk to sample broader or deeper. And so here we sample from heterogeneous anonymous walk, but then if coarsening, then we coarsen that. Then finally we append it. So the same methodology that we used before. And they'd use it for these data sets that have, most of them have 3 or 4 classes. And here you see C is the country, Q is the question, U is the user. You see the number of classes and number of edges. And now here they calculate Spearman correlation coefficients with p-values on stack exchange network. The stronger correlation is in bold. So these are the p-values. And this is the average accuracy for user classification on just a stack exchange network. They compare, for example, deep walk that I've explained. They compare struct2vec that I've explained in a different video, roll2vec, VD. All of them compare with this method. And you see the accuracy is improved. For example, from 2%, 20% to 40%. So this is the characterization visualization of the closest 5 users.